Hello students, welcome back. In the previous video, we did the first half of piecewise defined functions. We went through this problem, left hand side and right hand side derivatives, and then we had this kind of visualization. The first line is blue, and the third line is red, and the second line is this point. And the derivative computation, or this Newton quotient computation, was the slope of blue dashed line. And then part B, this limit computation, the right hand side derivative computation, was the slope of this red dotted line. And they share the same quantity 3, so the derivative existed. And equivalently speaking, f was differentiable at x equals to 1. And then we did this kind of problem. We have to find out a value where this function is differentiable or the derivative exists. Both left hand side and right hand side derivative exist and they're the same. And it turns out this is continuous. If you plug in x equal to 2 to both first line and second line, they're the same. So that's not the issue. Differentiability was the issue. The perfect solution is through Newton quotient computation, but this is really difficult to follow, even though it always works. If you use shortcut solution, there's a bit of a danger. It doesn't always work, but it's much simpler. Take the derivative, and at x equal to 2, set them equal. We get this equation, and the solution, well, that turns out to be the answer. If you see this kind of problem in Calculus 1 level, the shortcut solution will work. It doesn't always work, but in exam level it will work, so don't worry too much about it. I wrote both solutions because, well, what can I say? I'm the teacher. I have to cover everything like blanket. Students don't usually have to do everything, especially for exam preparation. This shortcut solution will do just fine. Visualization, last time we failed it because I was running too many programs at the same time. I just quit some problems. I just quit some programs and then it is working just fine. So let me show you. Kind of goes like this. So for left hand side derivative, we need this blue dotted line. For the right hand side, the graph itself is line segments, so we don't need separate line. And then do you see when they're lining up? Kind of hard to see. Well, when a is equal to -1, we have this alignment. When a is equal to 2, we have this perfect alignment. So at these 2 points, at these 2 a values, we have differentiability, otherwise not differentiable, not smoothly joined. Okay, let's go over to the last problem. This time continuity and differentiability put together. We have this kind of problem here, and find the condition for which the given function is continuous. Previously, continuity was already there, so no problem there, but this time you really have to work on it. So how do you do that? Plug in x equal to -2 for the left hand side limit. Plug in x equal to -2 here for the right hand side limit. Set them equal. Here it is. This is the left hand side limit computation. Plug in x equal to 2 to the first line. Simplify, we get this. The right hand side limit computation is this. Plug in x equals 2 to the second line and do your computation. Simplify, you're going to get the final expression. And then plugging in x equal to -2 to, again, the second line here, we get the function value because equality is included over here. The third line here is not really necessary as far as problem solving is concerned. Anyway, we have these 2 quantities, this one and that one. and setting those equal, we get this kind of computation. Turns out that minus 2a here and minus 2a there cancel each other out, and we get b equals -2. So the conclusion, this function is continuous if b is -2, otherwise not continuous. That's what we get from this computation and then that computation. Okay, so much for the continuity, and we found out that b is equal to -2. So for the differentiability, this is where we start. Plug in b equals -2 so that this is +6, and this one over here is just 2x squared, so we have to deal with this function. If you don't have continuity, then there's absolutely no point considering any kind of differentiability, so this is a necessary step. Okay, here we go. And in particular, f of -2, well, equality is here, plug it in, and then we get 10 minus 2a. As a matter of fact, both will give you 10 minus 2a. Okay, and then let's find out left-hand side derivative using Newton quotient. Here's a computation. Plug in -2 plus h in place of x to the first line, and then do your computation. Here we go. Break up parentheses, take the like terms and simplify, further simplify, and then please note that every term has h after cancellation, so the denominator is gone. We have a minus 4. That's the left hand side derivative. How about the right hand side derivative? Do the same thing to the second line, and what do you get? We get -9. Plug in x equal to -2 plus h, like this, and then break up parentheses and simplify. So early on, what did we get? We get a minus 4 and then -9. So setting these two equal, we get a minus 4 is equal to -9. We get a equals to -5. So that's when our function is differentiable. This is the perfect solution. Let's see, how about a shortcut solution? Okay, let's work it out. We just take the derivative term by term, piece by piece. Take the derivative here, we get 2x plus a. Take the derivative here, and then we get that. And then please recall that b is equal to -2. As a matter of fact, let me see. I could have plugged in b equals -2, but here in this solution I didn't bother. Just set these two equal to each other, and then we ended up with well, this relationship between a and b, and then you can plug in b equals -2 later. Well, you could have plugged in earlier, but I decided to plug in later. It doesn't matter. If you do that and then do your computation, in the end you're going to get -5. This is much easier solution compared with the Newton quotient computation. The defect or the shortcoming of this is this doesn't always work. So you have to be a little bit careful about this. But then again, as I said earlier, in exam level it'll work. So I do encourage this shortcut solution. By the way, here is the visualization. Let's see how this thing works. Yeah, there are two parameters, a and b, so we have these two. Let me see. What if I change my b value? You see, we have breaking. And we have continuity when b is equal to -2. Oh, let's stop this. Equal to -2. That's when we have this continuity. And let's change A value around. Continuity doesn't go anywhere because B value is now fixed at -2. But as you can see, we have cusp forming, and then we have smooth joining, and then further, and we're losing the differentiability. So if you plug in A equals -5, then we have perfect continuity and differentiability. But if I switch my A value around, you see a cusp is forming there. A cusp is forming there. And then of course if I change my B value, discontinuity is forming. Anyway, here is a visualization.